Okay, thanks a lot, David, and thanks everyone for inviting me to this workshop. Okay, my talk today is about how to use non-convex optimization to solve a low-rank tensor completion problem. Okay, so. All right. Okay. So this is joint work with my student Changxiao Cai, my Gun Li, who is going to join my group as a postdoc, my collaborator Yuxin Chen, and my colleague Vince Poole. All right. Okay. So since this is a workshop about tensor, so I'm going to skip the motivation part. I think everyone probably knows why tensor data is an important object for us to study. But one key thing that we need to deal with is how to reconstruct a tensor if we only have highly imperfect measurements about a large dimensional tensor object. Okay. So this is the kind of scenario that I'm going to focus on in my talk today. So imagine that I have a very large dimensional order 3 tensor, and suppose that I only get to observe a subsampling of the entries of the tensor. And to make it even worse, each entry that we observe might be corrupted by some random noise. The goal is to find a way to still reliably reconstruct the tensor, unseen tensor of interest. Okay, so in general, we know that this is impossible because we're doing subsampling unless we can exploit some low complexity structure that make things, at least information theoretically, possible. Okay, so throughout this talk, I'm going to focus on the very commonly assumed low complexity structure called low CP rank structure. Essentially, this is like saying that we are assuming the ground truth tensor can be decomposed into a superposition of, let's say, R rank 1 tensors. For simplicity of presentation, let me only focus on the symmetric case, but I'd like to let you know that our results actually easily extend to the asymmetric case. But yeah, the one bad thing about tensor is that there are so many notations there, so let me try to simplify things as much as possible. Okay, so I have a tensor T star, and it has a rank R structure, and I would like to find a way to reconstruct it. Okay, mathematically, let me introduce a few more notation which will facilitate discussion. So I'm going to assume the dimension of the tensor that I have is d by d by d. Okay, so think of d as something that's very large. I have a random subsampling of the entries of this tensor. Okay, so I have suppose I have a location set called omega, so that I'm able to take a measurement of an entry if the index of this entry lies within this index set omega. All right, okay, and as I said, each entry that I observe is corrupted by some random noise. And my goal is to find a way to recover both the unknown tensor T star and its low rank factors UI stars. Okay, all right, okay, so these are all the notations that I need. Okay, so why is this a challenging thing? So I'd like to remark that tensor completion is significantly more challenging than the matrix completion case. Part of the reason is that there exists, for example, a large gap between what is doable in the information theoretical sense and also what is achievable in the computationally feasible sense. All right. Okay, so let me quickly mention this, and probably many of you already are aware of this. So imagine that, let's say, okay, I'm focusing on the rank 1 tensor, so R is equal to 1. Okay, now suppose I have IID random subsampling. Okay, now how many random entries do I need to observe in order to reconstruct this tensor? It will be at least on the order of D, actually. So there's an information theoretic limit about D, or maybe sometimes up to some log factor. However, it is known that there is no so far there is no polynomial time algorithm that is known to achieve the statistical limit. In fact, there is no tractable algorithm that can recover the tensor if the sample size is below d to the 1.5. Okay, so this seems to be a big gap here. Okay, In fact, there are quite a few people, particularly in theoretical computer science, they claim that they conjecture that this gap is probably not closable unless we are able to solve something like p equals to mp.
The question is: this true for constant r already? Just the function of d?
Constant r, yes. So this is for the constant r case. Yes. Thanks. Yeah. So I'm actually. Let's simplify things. Let's assume r is equal to 1. Okay. So it's absolutely a constant. Okay. So our focus is not to break this computational limit because I don't really think this is possible unless you change the sampling scheme. But our focus is to say, okay, are we able to do as good as what we can hope for in a computational feasible sense? And as you can imagine, this is a very popular problem that has been studied by a lot of people. Here I'm listing a few examples here, and a lot of different kind of algorithms have been proposed towards solving this, including convex realization, spectral method, sum of squares hierarchy, non-convex optimization, a lot of them. Okay, so why is there still room for us to make improvement? Okay, so let me quickly summarize the prior art, assuming that the rank is a constant. So if there's no noise, okay, and there's a bunch of algorithms that have been proposed, starting from perhaps, like tensor nuclear norm minimization, okay, and 5 years ago, and then there's a group in Columbia and Rutgers that have looked at nuclear norm minimization. It's a very natural extension of the matrix nuclear norm minimization algorithm, but unfortunately, tensor nuclear norm is in general not computable in polynomial time. And as a result, this algorithm, even though this has a good statistical performance, it is actually an NP-hard algorithm. And so it's like intractable in general. Motivated by this, and then there are several other people start proposing that, okay, why don't we just try to look at non-convex optimization, looking at gradient descent in a careful way, probably initialized by some spectral method. Okay, and this result is good in the sense that the sample's complexity they achieved approaches the computational limit, which is good. Unfortunately, there's almost no computational guarantees in that paper, except that it said it converges within polynomial time. So it remains really unclear how does it perform in the computation in some large-scale problems. Okay, so and Andrea Montanari and Nike soon proposed a spectral method towards solving this, but spectral method alone actually is not able to solve the problem in the exact way, and also the way they do it has a computational complexity that looks like D to the third order. And also there's always this SOS kind of algorithms proposed for solving this. They are very good in terms of statistical performance, but they are known to be very, very slow. Okay, typically, their complexity is at least D to the 10th, okay, which is not really scalable to large dimension. Okay, so far the first table is about performance for the noiseless case. When we move on to the noisy case, much less is known. Actually, the first paper here provided some stability guarantee, but it turns out to be highly suboptimal. And also, even for the SOS case, if we look at random noise, the estimation error bound provided there is still far from optimal. Okay, so all of these motivates the following question, which we like to address today. Can we hope to design an algorithm that simultaneously achieve sample efficiency, computational efficiency, and statistical accuracy? So we are trying to find a way to see whether we can achieve all of these all at once. Okay, so the algorithm that we are going to look at is some sort of non-convex optimization. Okay, so let me start with perhaps the most natural formulation for doing this. Okay, so which is the least square formulation. Okay, imagine that I know I have a low-rank tensor to solve, and let's just represent it explicitly using the low-rank tensor structure. And I have several data which over this omega sampling set, and for every observed entry, I'm computing the square loss, and then I'm trying to minimize the square loss, which is a very typical least square formulation. Okay. It's some good thing. Actually, it can be shown that this is a very good strategy, actually, if you can solve the problem. Okay. If you can find a global minimizer, we are able to show that this actually is statistically efficient algorithm for solving the tensor problem. The bad thing is that it is a highly non-convex problem. Okay, so it involves a degree 6 polynomial in the decision variable. So in general, this is computationally intractable to solve. Okay, but this is a good starting point. But why don't we just try to use whatever our favorite algorithm and just to try to run it and see how it goes. All right. Okay. So perhaps one of the most natural algorithm for us to do is to look at gradient descent. Okay. Everybody likes gradient descent now. Okay. So and we probably need a starting point, but let's just assume that we are initializing the algorithm randomly. Okay, and we start with random initialization, and then we run gradient descent until it converges. Why do we think this is going to work? Actually, because there are a lot of success story about gradient descent with random initialization. For example, in our prior work, we showed that for problem like phase retrieval, randomly initialized gradient descent works perfectly. Okay, so why don't we just try it? Unfortunately, I would like to argue that actually this turns out to be a not so good algorithm to use. Actually, it's in stark contrast to the matrix case or the phase retrieval case. In fact, there's a conjecture that this algorithm does not work unless the sample size is very large, exceeding d squared. Why is this true? Let me try to quickly point out what is the issue of randomly initialized gradient descent. Okay, suppose that we have, let's say, the sample size approaching the computational limit, which is d to the 1.5. If you start randomly, and then if you check the search direction at the beginning, if you compute the expectation, actually, it is a good direction. Actually, if you compute the expected direction, you can actually show that it is making progress. It is taking you a little closer to the ground truth, which is a desired direction. The issue actually arises because of the variability or variance. If you compute the variance at the initial stage, you can check that the variance of the search direction becomes substantially larger than the expected direction square. Okay, some sort of mean square. And this is a bad thing because this is somehow saying that even though you are on the expectation, you are moving towards the right direction, but the uncertainty is too large that basically kill your direction. In fact, the progress that you are expected to make, it's completely buried in the variance, which is in stark contrast to the matrix case. In the matrix case, even though you still also have variance, actually the variance is well controlled by mean square. And this can be reduced if the sample size exceeds d squared. So if you have many more samples than the computational limit, things are fine. Variance become well controlled. That's why your algorithm starts to work. Okay, so let me put everything back to this picture. This is a message I'd like to say here is that randomly initialized gradient descent is only expected to work if the sample size is larger than d squared, which is, as you can see, still much larger than the computational limits here. Now the question is that if our goal is really to approach a computational limit, what should we do? Okay, so this is so we propose an algorithm in our work to address this issue. Basically, the algorithm is also going to be like a gradient descent type of algorithm, except that we are going to use a much more clever initialization rather than just running in random initialization. Again, in contrast to the matrix case, initialization turns out to be a crucial part for tensor case. Okay, so in the initialization part, I have very, very informally, I have two substages. The first substage, I try to estimate the subspace spanned by all the tensor factors. So rather than the individual factor, in the first step, I try to estimate only the subspace. And this can be done using some sort of classical spectral method with unfolding. And then in the second substage, I need to find a clever way to disentangle the individual factors from this subspace estimate, okay? And after that, I'm hoping that I get the good reasonable initialization. Hopefully this is strictly better than random initialization. And then I can run gradient descent until it converges. So why do we think this is a good algorithm? Just in case you're not familiar with recent advances in non-convex estimation, the rationale is very simple. Even though we are dealing with non-convex optimization formulation, if you are able to get the good initialization that is sufficiently close to the solution, maybe locally the problem, the optimization landscape is not that bad. Maybe it enjoys some sort of smoothness or strong convexity, at least in the restricted sense, and which give us hope that maybe the algorithm can converge in a fast manner. Actually, this is the main motivation for the recent studies of non-convex estimation algorithms.
Yeah, in the chat, Joseph is asking partly my old question, whether you assume that R is order of 1.
Yeah.
Or in particular, if it's smaller than B.
Yeah.
Yeah. Mm-hmm.
Yeah. So throughout this talk, I'm going to focus mostly on the case when R is very small, on order 1. We have more general results, but when R gets grows, actually the result become no longer tight in terms of its scaling in R. So that will require some future work to further refine. But throughout this talk, let's focus only on the case when R is small or order 1, but which okay. So all right. Okay. So all right. Okay. So let me talk a little bit more about the initialization. Okay, so what kind of strategy we're going to use for initialization? So in the first step, I'm going to estimate a subspace, as I mentioned. And the subspace is a subspace spanned by the unknown tensor factors. And how to do it? We do a very simple thing. Okay, we're going to matricize the tensor data. All the observation we have, we matricize it into a very fat matrix A. And then let's try to compute the rank R column subspace of A using the ground matrix AA transpose with proper handling of the diagonal entry. Okay, so you might wonder why this is a good strategy to even start with. As you can imagine, matricizing the tensor actually destroys a lot of tensor structure, which might not be a good thing to do from an information theoretic sense. But I would like to argue that this is still very different from just destroying the tensor structure, because after we do the matricization, the only thing that we want to do now is to estimate the column space of A. And the column space of A, even though we won't be able to recover this entire matrix A using this method, but we still probably have enough samples to estimate just the column space of it, which is a much lower dimensional object compared to the entire matrix A. Okay, so this is a very naive but it turns out to be a very simple strategy that works. We do unfolding, we do and then we compute the column space using a spectral method, and it turns out to be a good estimate of the subspace we want to estimate, as long as the sample size exceeds the computational limit. After this, after we get the subspace estimate, let's use sub. The next step is to try to see whether we are able to disentangle or extract out estimates for individual tensor factors from this subspace estimate. And this turns out to be a very difficult one. And the way we do it is that actually after we get this tensor subspace estimate, what we're going to do first, generate the random vector G from this subspace. Okay. So we already know it lies within the subspace, but we just should generate some random vector from this subspace. And then we project our tensor along this random direction. And it turns out that with high probability, there will always be one direction that will stand out from this projected version of the matrix. And that, as long as there's one direction that stands out, and then you actually a simple spectral method, which is basically computing the leading eigenvector of this matrix, allows us to get some estimate about this direction. And we can do it one by one. Every time we just regenerate a random vector, estimate another tensor factor, and continue until we finish everything. All right, okay, so this is about the second step. Okay, so now I'm done with an informal description of my algorithm. Now let me try to convince you that this turns out to be a good algorithm. Okay, so to do so, let me impose some assumptions in order to make the algorithm works. First of all, we are assuming random sampling. That's sort of basically the same assumption as what people use for matrix completion. We're assuming each entry is observed independently with probability P. We assume random noise such that each observation is corrupted by some zero mean sub-Gaussian noise with variance at most sigma square. We impose some conditions on the ground truths. First, we assume this is very low rank. Rank is a constant. It's well conditioned, so all the tensor factors have the same order of magnitude. We also assume some sort of incoherence condition for tensor. Basically, we need each tensor factor to be delocalized, and also any pair of them are not too aligned with each other. Okay, so with this, I'm able to present my theorem. Okay, so UT is my estimate of the individual tensor factors. TT is my estimate for the whole tensor. There's just one ambiguity here that I need to mention, which is this pi thing, which is like a permutation. But since I'm estimating a group of individual tensor factors, I won't be able to tell which one is which up to global permutation. But okay, but except for this global ambiguity, this is what I can say. Okay, I'm able to estimate U star, the ground truth tensor factor, with this statistical accuracy. I'm able to estimate T star with this accuracy. And this is for the Frobenius norm. I also have some entrywise norm here. So L infinity norm. Okay, so so far I've just given you a few equations. Let me try to interpret them to tell you that these are actually some appealing theoretical guarantees that we like. First of all, let's look at this rho factor. Rho is some constant strictly bounded away from 1. Think of it as some rho as like 0.8, for example. So basically, this means that the algorithm converges linearly or geometrically fast until an error floor is hit. Second of all, the sample size required here is just like a polylog factor away from the computation limits. Okay, so this is a near optimal sample complexity among all the computationally feasible algorithms. The third message is that, okay, let's look at the error floor. Okay, just remind you that sigma is a variant or standard deviation of the noise. If sigma is is 0, which is the noiseless case, basically it means the algorithm converges exactly to the ground truth. Otherwise, if sigma is non-zero, and we can also show that this turns out to be the level of the minimax lower bound. Okay, so essentially this is saying that we are able to approach a minimax optimal limit using this algorithm. And this is true for both the Euclidean norm error and entrywise error. Okay. All right, okay, so we have some small, a few numerical experiments to show that this actually is an algorithm that can be run in practice. On the left panel, we show that the algorithm really converges geometrically fast until an error floor is hit. Here, the y-axis is plotting on the logarithmic scale, so this really means linear convergence. On the second panel, actually, we show that the algorithm, the quality of the solution degrades gracefully as the signal-to-noise ratio decreases. There's one thing that I like to emphasize is that our theoretical guarantees do not rely on any sort of sample splitting. Okay, you can reuse, you are allowed to reuse all the samples across all the iterations. And this is a good thing to do because a lot of people in prior work for matrix analysis, they use sample splitting mostly to help analysis. But as a practical algorithm, it wastes data. But our results allow us to reuse all the samples, which is particularly useful in some sample-starved applications. Okay, now the question is that, as you can imagine, how it becomes much more fairly complicated to deal with the statistical dependency across iterations, and what should we do? Okay, so I don't think I have enough time to talk about any of the analysis, but let me just give you some of the keywords underlying our analysis, which is the so-called leave one out decoupling idea. This is a kind of strategy deeply rooted into probability theory and random matrix theory, and actually statistical physics as well, which we have used it recently to tackle a lot of a variety of different problems, starting from spectral method, non-convex optimization, and recently reinforcement learning. We have recently finished a monograph on spectral method where we include one chapter discussing this leave one out analysis, just in case you are interested in this. And very, very roughly, at a very, very high level, this analysis is basically doing the following. I have a lot of observed data. Let's just drop a small fraction of it, okay? And since I'm dropping only a small fraction of it, we expect and then we can rerun the algorithm, and the new iterate is expected to be quite close to the original one because I have not really dropped a lot of data. But since I'm dropping some data, I'm able to get statistical independence. At least we can show that the new iterate becomes independent of the part of data that we have dropped. Okay. And this allows us to show some sort of weak or local statistical independence. And also because there's some stability argument, we can show that the new iterate is very close to the original one. So this allows us to, in turn, show that the original iterate is also only weakly dependent on the data. Okay. All right, okay, again, this is a very complicated thing to do. I don't want to go into detail about this. Feel free to talk to me offline about if you're interested in this kind of analysis framework. All right, how much time do I have?
So officially the time is up just now, but there was at least one question. So if you have a few slides to go through quickly, do it now.
Yeah, so maybe let me spend another 2 minutes to quickly mention the rest of this, and then if you have there are questions, I'll take questions. All right. Okay. So one other thing that I like to mention is that so far I have shown that the algorithm is fast, it's sample efficient. Is one more thing that we can show using the same algorithm is that we are able to even assess the uncertainty of our estimate. Basically, we can use our estimate to build confidence intervals in the very precise and valid way for the unknowns. Okay. And why do we care about uncertainty quantification? Actually, this is a very important thing to communicate to the user. If there is noise, if there's missing data, you want them to know how good your estimate is and how much confidence you have about the estimate you return today. Okay, so we are going to just try, but this is a very difficult thing to do because we are solving a non-convex problem. It's usually very difficult to develop a distributional theory for the non-convex algorithm. But fortunately, the Lee-Van analysis that I mentioned allows us to do so. So let me just quickly mention what we can say. For each of the estimates of the entry, we can show that our estimate turns out to be a nearly unbiased estimate of the ground truth. And with the turns out the error turns out to be Gaussian distributed, and its variance almost matches the Craméral lower bound. So in some sense, this is asymptotically optimal distributional theory, which in turn allows us to build confidence interval. So now we are able to build confidence interval such that some of the highlights here is that we can build it in a completely data-driven way. You don't have to know a priori what the noise level is. You don't require the noise levels to be identical across locations. So this actually turns out to be a fully adaptive way to build confidence interval, which is has a lot of practical advantages. And finally, I'd like to mention that after you get the precise distributional characterization, now you can come back to estimation, and then you can actually even pin down the pre-constant for the Euclidean error. Okay, so now we can show that for the entire class of, incoherent low-rank tensor, the estimation accuracy of our algorithm is 6 times sigma squared times r times d over p, which turns out to be the Craméral lower bound, including the pre-constant. All right, okay, so this is everything that I like to say here. Non-convex optimization is a very good strategy. It's fast, it's sample efficient, and it allows you to get fine-grained uncertainty quantification. The results are summarized in these 3 papers. Thanks a lot.